So I'm going to try to actually, before going to Bayesian regression, to just give you some of the basic things that you already heard last week. So this is obviously a supervised learning problem, and let me just go to slide 7. So what we're given is a sequence of training data points that you see with these circles here, if my pointer works, okay? And so we're trying to fit a function, and at some x's I give you what the response from this function is. We don't know what the function is, so the function is actually this curve, right? But we don't really know it. So in principle, the data points that I give you have some noise on them, and we try to figure out really what the function is, okay? And the objective is not just to fit these points correctly, but the objective is to be able to pick up a new x, let's say this x, and say what the value of the function would be. So the task of actually fitting the data well is not really too relevant here. Yeah, it would be nice if the training data fit well, but more importantly, we need to be able to do predictions that they're accurate. So in the context of not statistics or anything, if you think of curve fitting, you are trying to compute these coefficients W0 to Wm with, so you're trying basically to approximate how this function may look like. And in this case, you take it to be a polynomial of order m in x, right, of this form. And you say, maybe if I can compute these coefficients in a way that I can, it fits my training data, then I can use this equation for any x to tell you what y is. So that's the traditional way of looking at these things. Now, the way that you do this fitting, mainly from your earlier courses, would be to actually look at the training points and see how much error the function that you use does. And you say, I'm going to find W, so I minimize the square error. All right? And the square is indicated here. All right? So Tn is the training data, these blue dots that you see, and y of xn and w is what you're actually predicting. So in essence, you're minimizing the square of these lines that you see in the picture. Okay? Now, if I can go back, if you put this nice expression on this square loss function, you're actually getting a very nice algebraic problem for w. So you should actually do the algebra. But you get a very nice problem where this matrix A has these components for each data point that is x to I plus j. Okay? The details are not very important, but you should definitely not trust what is on the slide. And as an indication that you understand, you should do the optimization problem. So substitute here the polynomial, take derivatives with respect to w equal to 0, and you get this nice system of equations that you can solve for w. So let's see what the problem is. We're going to assume that the actual function that generates the points is this particular sine function that you see here. And so we're going to fit these points with a polynomial first of order 0. So that would be a straight line. So when you look at this straight line, right, so you compute basically this coefficient W0 only. When you do the optimization, it doesn't seem to do any good job. All right, so the model is very simple. If you use m equal to 1, you get a straight line, a little bit better. If you use m equal to 3, way better. And if you use m equal to 9, as Nick told you on hopefully on the lectures last week, you overfit. Okay, so this, in the context of interpolating between the training data points, looks extremely good. But something like that, if you try to do predictions, the predictions will be garbage, because this curve that you computed here, it really doesn't fit the function well. What it does is it fits the points accounting for the noise in each point, okay? And the noise is not something we really need to fit on. So this is what is called overfitting. So remember, m equal to 9 is really bad. Now, a good way to see this, and this type of plots you need to do in machine learning, is if you compute the root mean square error, and I write the root mean square error as, you remember E, if I can go back so I can remind you, E is this error function, right? That's what we discussed, okay? So E is that error function. So if you multiply this by 2 divided by n, you take square root, this is what I call here the root mean square error. So if you plot this for the training and the test data that you have, you observe a behavior that looks like this. So let's pick up the training data, this blue line. You can see as the order of the polynomial increases, all right, the training error starts decreasing, then it stabilizes, and then of course for polynomial of order 9 becomes 0 because you fit everything perfectly. Okay? Now, obviously, you know that would be sensible to select an order of polynomial somewhere here, okay? But if you take a polynomial of high complexity, you overfit, and you can see the fact that you overfit when you look at the training error, and when you look at the testing error. So the testing error follows the same path as the training error. It has a flat region, but then you notice when you go from m equal 8 to 9, it actually explodes. So you fit the training data very well, but when you do predictions, the predictions are very lousy. So it's very good to actually do diagrams like that because immediately tell you something about the polynomial order selection that you have to do, which is really a model selection problem. Okay. Something interesting, and by the way, I know lots of you read the slides. Don't play with the computer programs. You semi-understand what's going on, but if you actually run this computer program, assuming that it runs, okay, you will realize that for m equal to 9, the coefficients that you get are very big. And as a matter of fact, they're plus minus big numbers. And you notice the polynomial of order m equal to 9 is oscillatory, right? If I can go back, you can see here, right? It goes down and up, etc. And usually this implies that the coefficients that you get are plus minus big numbers. All right, this is multiplied by 10 to the 6th. So when you overfit, the coefficients get very big, they become very big numbers. So somehow you can think a way to control the complexity of the model is to restrict the coefficients not to become very big. Okay, and this is what we will discuss today. That's what we call regularization. Okay, it's a term you need to learn to pronounce in English, and you need to understand what technically means. Regularization. Okay, before we go to regularization, let's see something else that is very interesting with this classical way of fitting data to some polynomial. So before, if I remember, we had, let me guess how many points we have here. How many data points are those? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, let's say 10 data points or something like that. So if you actually increase the data points, all right, to 15, and you use a 9th order polynomial as before to fit these 15 points, you see that the overfitting is not as significant as before. All right? So the more data you have, the less severe the overfitting problem becomes. Okay? And I want you to think that philosophically this is troubling, right? Because you are trying to compute a model to fit the data and in essence do predictions. But here what we say is the complexity of the model that you compute, it depends on the amount of data you have. But the complexity of the model, you know what it is? It's a sign function. It has nothing to do with how many data points you have. All right, so there is an underlying complexity And it's nothing to do with how many data points I give you, but this technique here, this fitting we did, it tells you if you use more data, the overfitting is actually not as significant, which means the complexity of the model is not as high as before. So adjusting the complexity to the number of the data points you have is not a good thing to do. It's not sensible. It doesn't make sense. Okay? But this is sort of your standard way of fitting this type of data with some parametric model. And you can see here, for example, if I give you 100 data points and you try to fit a polynomial of order 9, it looks to me like a perfect fitting, right? So, you know, the more the data points, there is really, for this case, there's no overfitting. It looks perfect, all right? It looks perfect. But the fact that the complexity of the model depends on how much data I give you in the training set, this is not good. Okay. Obviously, there is a statistical interpretation of this overfitting, and I want you to remember that the way we computed the parameters is by posing that minimization of the square error, which really led to a least square solution. So what I want to actually convey the message here is that this least square solution that we computed up to now, it's basically the same as computing what we call the maximum likelihood estimate for this problem. Okay? And I will elaborate on this in details. So in essence, the overfitting problem and heavy and complexity that depends on the data, on the size of the data set, it's the same pathology that you get when you use maximum likelihood. Right? So when you use maximum likelihood. So the classical way of computing the maximum likelihood and doing predictions with that has the same issues as least squares. As a matter of fact, the two things are identical. There's no difference. It's exactly the same thing. Okay. So as I suppose you heard last week in the lecture, when you try to do a Bayesian you try to build a Bayesian regression model, you will realize that there is no overfitting, okay? And in essence, you're actually controlling implicitly the complexity of the model, okay? So the number of effective parameters in the model adjusts to the data size automatically, all right? So we will see this today, hopefully, on how is going to happen. Okay, so before we go to statistics, how do you actually you control the complexity of the model? So up to now, the least squares problem was minimizing this square error. And we mentioned that if you use m equal to 9, the coefficients become very big, plus minus signs, very big numbers. So what you do is, rather than just minimizing this square error, you're also adding a regularization term that controls the magnitude, the magnitude of the coefficients w. So this w that we see here with these brackets, it's the norm of w, right? I'm assuming that w here is a vector. So this controls the magnitude of the vector w. So effectively it says, minimize the error, but at the same time, keep the complexity of the model small. Something very important, okay, for those who have seen ideas of optimization with constraints in your undergraduate studies. Regularization is not the same as penalizing, is not using penalty terms. So this lambda here is not a very big number. It's usually a tiny little number. All right, and I'm going to tell you the analog, maybe that you want to go in your office and test this with MATLAB programs. Take a system of equations 2 by 2 or 3 by 3, ax equal to b, where a is singular, so it's not invertible, and go and put a little, very tiny number in the diagonal of a, and you will see suddenly you can actually invert a. This is what is happening here. All right, so effectively, the system of equations that we get is not well posed by doing this optimization, And now what we're going to do is we're going to add this regularization term that is going to control the magnitude of W. And if you want to see the similarity that I mentioned with adding a small number to the diagonal, you can actually do the minimization problem. So you can put y to be summation of wi to x to the power I. So you can put your polynomial there. You can explicitly write this in terms of w1 squared, w2 squared, etc. Take derivatives with respect to w. And the system of equations looks like before, but notice the matrix Aij in the diagonal has plus lambda. Can you see that from those equations? In the diagonal it says go and add a very small number. All right, so you make basically that matrix A that we had before well posed by adding a very small number that comes from this regularization term. Okay? So now you may ask me, how do I select lambda? And this is not a course about regularization methods and inverse problems. All right? So right now, lambda will just say controls the complexity of the model. And as a matter of fact, if you want to do a safe way of selecting lambda, you can try to see how the system behaves. You know, you can plot your results as a function of lambda, and then you will see there is a very big range of values of lambda where the results don't seem to change. So you can imagine if you go on the diagonal and add, let's say, 10 to the minus 8 in every diagonal element, you get some answers, then you get 10 to the minus 9, nothing changes. 10 to the minus 10, nothing changes, the same results. So you know there's a whole range of lambdas that do the job. Okay? All right. Now, this is one form of regularization, and this is based on the norm of W that we use, is L2 regularization. And I will show you today other forms of regularization that are extremely important in machine learning, all right? But right now, this is what we have. So if you go and add a very small regularization on the problem with the few data points that we had before, and I'm assuming m equal to 9, so the log of lambda is minus 18, so lambda is a very small number, you can see suddenly there is no overfitting. Right? So we immediately know there is a way with regularization to control the complexity of the model. Okay? There is a way with regularization to control the complexity of the model. Now, if you use huge regularization, right, can you guess, if you look at this and you put lambda a huge number, what's going to happen? I mean, you try to minimize this plus that. So if lambda is a very big number, what will happen to the W's? There will be 0, all right? So, so the only thing you will get actually, so I mean, for this particular case, from the whole, let's say, 9th order polynomial you use, only maybe the constant term and the linear term will remain there, all right? And if you keep increasing, you will actually get only the constant value, even though maybe I will mention this on another lecture, when you approximate this function with a polynomial, right, or anything else, you don't regularize the first term W0. Okay? This is a tricky part. You only regularize W1, W2, etc. You don't regularize W0. Okay? But right now this is unimportant. The idea here is by using very high regularization, a lot of the W's drop down to 0, and you get a very simple model. All right? And a very simple model cannot do the job of fitting the data or doing correct predictions. So if you want, as I mentioned, you don't really know anything about regularization, and you want to figure out on how to select the right parameter, what actually you can do is you can take the root mean square error that I indicated before, and you can compute it for the training data set and the test data set for different values of regularization. So the horizontal axis here is the log of lambda, and you can immediately see that there is a flat region all right? There is a flat region where the errors both for the training and the test data set don't change. So effectively, any value of lambda in this region would do the job. Okay? All right. So just remember, regularization controls the complexity of the model. And right now, when I talk about complexity of the model, it really implies what's the order of polynomial, because that's the type of scene we have seen. Okay. So progressively, we're going to start doing, you know, the Bayesian version of regression. And I can tell you ahead of time, all right? So somehow the slides are a little bit mixed up to slowly introduce you to the Bayesian paradigm. So in the Bayesian way of doing regression, we're going to assume that the coefficients W, they're not deterministic. We're going to make them random variables, all right? Which means we're going to postulate a prior on W, and we're going to have a likelihood model and compute a posterior on W. And then we're going to use this posterior to actually do predictions. So there's going to be some algebra necessary to do this type of calculations. And I'm going to convince you, when you do things the Bayesian way, there's no overfitting. Somehow, the number of effective parameters, as I mentioned before, is automatically controlled for a given training data set. Okay, so let me go and do some elementary calculations that maybe you already have seen in your earlier classes, maybe not, but I want to make a connection of maximum likelihood estimation with least squares, right? That's what we have seen up to now. So the easiest way to see the maximum likelihood estimators is to consider a trivial distribution, in this particular case a Gaussian, with mean mu and a variance sigma square. So I'm going to give you n data points coming from this Gaussian. So the likelihood, all my samples are IID, so this is my likelihood. And if you take the log of this, the product becomes a summation, and eventually when you expand, right, so you're going to get these two terms from the, you know, this normalizing factor, you're going to get those two terms, and then from these exponentials, you're going to get the summation of xn minus mu squared. Okay, so this is the likelihood for a Gaussian distribution. Now, can you actually, if you actually think, right, the problem of estimating the parameters mu and sigma square, immediately I look at this function here, it looks very much like the function we had before, right? It's a square error, right? And that's where mu comes. So if you want to maximize the likelihood, isn't it the same as minimizing this term? Right? Which is not very much, it's the same thing as what we did with least squares, just a little bit, the situation is a little bit different. So if you take derivatives here of the log likelihood with respect to mu and sigma square, these are the estimates that you get, and I want you to remember them for the rest of your lives, because everything is referred back to these two estimates. So these are just not another formula, are extremely important calculations. So you can see that the MLE estimate for the mean is the empirical mean, all right? And the MLE estimate for the variance is the empirical variance, but notice is the variance of my data set with respect to what estimate is here? The MLE estimate of the mean, not the actual mean. And that's the source of overfitting, and that's the source of the problems with least squares. Again, this is the empirical mean is the MLE estimate for the mean. The empirical variance, all right, is the MLE estimate for the variance. But you notice this MLE estimate for the variance is the variance of the data xn with respect not to the true mean, but with respect to the MLE estimate of the variance. I'm sorry, the MLE estimate of the mean. Okay? So why is that important? I am going to give you the formula. So if you actually, if you look at these formulas, all right, in a, sort of in a non-Bayesian way, can you appreciate that these estimates are actually random variables in some way? Can you tell me why I may call both of these MLE estimates to be random variables? This is in a non-Bayesian way now I'm thinking. Can you see why? So I calculated this. Why can I call this whole summation a random variable? Why is that? I mean, I see there summation of xi divided by n. So what makes this, in a frequency setting, what makes this a random variable? Remember, we selected n data points xi. These xi points are what? Coming from a Gaussian. Right? So the randomness comes basically from the underlying distribution of the data. So if you think, so that these are random estimates because xi is random, if you take the mean with respect to the data set, to the distribution of the data of the MLE estimate of the mean, what's the mean of this? What is the mean of its xi? Xi comes from that Gaussian that has a true mean mu and a true variance sigma square. So what's the true mean? What's the mean of xi? Xi comes from a Gaussian that has a mean mu and a variance sigma square. Those are the exact mean and variance. So if I take the expectation of this, what's the expectation of xi? It's mu. So basically you will see immediately that the expectation of the MLE estimate of the mean is mu, and this is what we call in statistics that the MLE estimate is an unbiased estimate. Right? So its mean, it's actually the true mean. All right? It's an unbiased estimate. If you do the same thing for the expectation of the variance, so here what you will need is, when you expand the square, you're going to need to compute the expectation of xi squared, all right? But also you will need the expectation of xi times xj, okay? So when you do the calculation, it comes that the expectation of the MLE estimate of the variance is 1 minus 1 over n sigma squared. So it's actually less than the true variance. So the variance, the MLE estimate, is a bias estimate. It is not equal to the true variance, right? You can see from this expression here. And by the way, the only thing that you need to prove this is what I just mentioned before, all right? I give you the two equations. You look at them, you dream about them, and you see that there is really no algebra needed. When you expand this, you actually get that the expectation of the MLE estimate for the variance, it is not equal to the true variance, it's less. And that's exactly where all the problems with least squares and MLE estimators come. From the fact that the estimate for the variance is biased, and effectively everything comes from the fact that in the calculation of this MLE estimate for the variance, this mu here is not the true mu, it's the MLE estimate of mu. Okay? Now, let me show you a picture, which is a wonderful picture from Bishop's book that demonstrates graphically what the problem is. Suppose that I give you 2 points, okay? And I ask you, so these are my 2 data points coming from a Gaussian, all right? And I ask you to compute the mean and the variance of the Gaussian, right? So I give you 2 points, and you need to fit them to a Gaussian. And I ask you, what is the mean and what's the variance of the Gaussian? So if the 2 data points are what is here, will you agree with me that the actual Gaussian that you will get will look like this? I mean, the mean is going to be there, right? And the variance is going to be something like that. This would be the MLE estimate, basically, that you get with the 2 data points. Now, I can tell you that these 2 blue points come from a true Gaussian that looks like this yellow curve. Very different from what you see from the predicted. So this red Gaussian is a Gaussian that has mean and variance, the MLE mean and the MLE variance, computed with 2 data points. So I do the same thing now. I give you 2 other data points. All right, here they are. So will you agree that the new Gaussian will be this, right? That's your estimate. And all the 2 data points, it will be like that. So if you were, again, a frequentist, there's nothing Bayesian on anything that we discussed now. You know, if you look at the mean of the 3 Gaussians and you average the 3 means, I think it will approximately come to be correct. Can you see that? Right? If I take this point there, the mean of this Gaussian, right? You can think of this being on the minus side, plus this Gaussian, plus this on the plus side. It will actually give me the mean of the true Gaussian, approximately. But if you average the variance of the 3 red Gaussians, what do you get? You can immediately see that it's an underestimate of the true variance of the true Gaussian that is widely spread. Can you see that? Right? If you look at the variance of the true Gaussian, it's huge. Right? But, you know, this is what you will get if you average the 3 variances. Okay? So the variance is underestimated. Okay. So we're going to start thinking on how to address these problems. And again, I am going to start throwing ideas on how we're going to do it. But I still, you know, I will reach that point progressively, slowly. Okay? But I want to tell you how we're going to try to model this problem. So we are... you know, so our interest is basically somehow to be able at any given point x, right, to be able to do predictions and say what the predicted value of my system is, and I call the predicted value here t, okay? So what I'm going to do is, before we fitted the data to some polynomial, all right, to some regression function, now what I'm going to do is I'm going to take that regression function and make that regression function to be the mean of some Gaussian response at that input x0. What does that mean? When I'm trying to make predictions at x0, I'm going to allow my predictions to be probabilistic, and the mean of the probabilistic response is going to be the value that we had before on the deterministic methods. So this is my regression function, right? So my regression function will actually represent the mean response at that given point. So we're going to take that at a given point. The answer is not a one number, it's a distribution. And what we considered before with these squares, it's actually the mean of that distribution. Okay? So we are adding sort of more flexibility to the model, so we will see how this paradigm is going to work. And obviously this Gaussian is going to have some standard deviation sigma, so there is a spread here of 2 sigma. So we will see how the whole thing is going to fit in. So this is my regression function that you can take it to be identical to what we had before, written as in terms of these parameters w. But now this regression function is going to define the mean of the response at a given x0. Now, there is a lecture that is posted on the course website, and there is a derivation of it. So I'm only going to mention this once and for all. Okay. If you try to pose the problem deterministically with a quadratic loss function, right? And I don't want to, like what we had before with least squares. then what I mentioned before formally, you can write it as follows. For a given x, the expected value of the response for a given x, it's actually the regression function. So I want you to think what I described, that this regression function is actually the mean response. That is very much affiliated in a deterministic setting with a quadratic loss function. So if I had some other sort of loss function, you may get a little bit different things. But for what we will do today and the lectures this week, effectively this is what we're going to use. Right? That for a given x, the mean response is the regression function. Okay. Now, let me start slowly now, since we talk about the regression function. Let me generalize things a little bit, okay? And so before, if you remember, x was a scalar, and I had w0 plus w1x plus wm times x to the power m, etc. Okay? Now x is a vector, right? So we're going to actually fit a function in many dimensions. So x can be 3-dimensional, it can be 10-dimensional. I mean, you need to do regressions in high dimensions. And in real scientific applications, x can be 2,000 dimensional. Okay? So what we're going to do is we're going to actually write the regression function in the following form. W transpose phi of x, all right? W is a vector, and phi of x is some future function of x. And I will give you examples on what those can be, right? But somehow, this will allow us to introduce some basis functions of x and generalize the regression function from being literally W transpose x to actually being W transpose phi of x. Now, the functions phi of x can be nonlinear in x, right? You can put anything. You can put sine of x1 times sine of x2 squared. But what is important here is that the regression function is linear in W. That's why we still call this a linear regression model. Right? So the fact that you use nonlinear basis functions doesn't mean anything. The complexity is the same because the model is linear in W. So actually, there will be zero complexity to be introduced in the analysis by using this because the model is still linear in W. So you are making it fancy, right, by allowing these nonlinearities in X, but that will not add anything to the complexity of the overall model. Okay? And you will see this shortly. The coefficient here, W0, is very important, and it's called the bias term. Okay? And somehow when we do these regression models, you have to treat it a little bit carefully. In essence, you need to, when you penalize the model for complexity, you need to penalize the coefficients W1 to Wm minus 1, not to penalize W0. It doesn't add to the complexity of the model. Okay? Still, however, when I do the analysis, I'm going to put everything together. But when you write a computer code, somehow you have to do some special treatment for W0. Okay? So I may give you that as a homework. And it's already sampled in the slides as well. So what type of functions can you use for this basis functions phi? You can actually use what we had before, right? So you can use monomials in X if it is a one-dimensional problem. You can use Gaussian basis functions. You can see here lots of Gaussians with a given spread, with a given standard deviation, if you like. And these are normalized Gaussians, right? They're Gaussian. I mean, I call them Gaussian. Lots of people call them square exponential basis functions because they don't have the normalization factor, okay? But they do look like Gaussians to me. I'm going to call them Gaussians, okay? So they look like that. You can actually, I see there's another base function here. Sorry, we said that. You can actually use sigmoids, all right? These are the sigmoid functions, and the sigmoid function, in case we have not seen this before, sigma of A is 1 plus divided by 1 plus e to the minus A. All right, and you can see actually the sigmoid function goes from -1 to 1. So it's of very significant importance in many tasks, especially classification problems. But the way that I do here is I use the sigmoid centered at mu j, all right, with some scaling s, okay? And I pre-select those for now. All right, so you can use sigmoid basis functions. Now, there's only one guidance I'm going to give you about basis functions. The basis functions that you use when you do regression problems have to be of what I call of local support. That's the buzzword. So can you tell me what basis functions of local support means? When I say the word of local support, what does that mean? I mean, look at this Gaussians, right? Why do I, even though, Gaussian says, they go slowly, or even faster to 0 at infinity, what does it mean? Look at them. What does it mean they're of local support? So if I take a Gaussian center of this location, it only influences things what? Around that location. All right? So effectively, this is, we don't, the things that you learn in, in mathematics and say, I'm going to use polynomials, or I'm going to use Legendre functions, etc. They're not good for what we do here. We need functions of local support. All right? We need basis functions that only influence the response around their center. All right? We don't want a basis function here that is influencing what's happening down there. We only want the functions there that have, their support around that point to be useful for predictions. So basis functions of local support is the key ingredient in what we're looking. Okay. So again, before I introduce you a potential probabilistic version of regression, and I mentioned this regression function that we saw before is going to become now the mean of some Gaussian response at its location x. So the same thing that I did by introducing basis functions for this regression function, I can extend this to the probabilistic model, and I want you ahead of time to actually appreciate the way this probabilistic model is going to look like. So if you look at the second equation, it says the response at the given x is going to be this red line that you see here, defined in terms of these parameters w, plus some noise that is a Gaussian noise. Right? Remember, you look here at the response at this point x, it's a Gaussian, all right? So you can get multiple things with some noise, and this noise here has a precision beta, all right? So the inverse variance beta, we have no idea what beta is, but there is some Gaussian noise, but this is the mean response because the mean of the noise is 0. And what do we do for the regression function? We use what I just described before. We're going to use some basis functions of x, phi of x transpose times w. Okay? So we are basically, when we're ready to do probabilistic models, we can actually write the response at any x as a Gaussian, with mean to be the regression function, and some variance beta minus 1. Okay? Or a precision beta. All right. So let me go back now to this regression model, right? And revisit the context of maximum likelihood estimation for our regression. So let's suppose that I give you some points xn, all right? So I give you these points xn, and I give you the response tn, and you're supposed to fit me a regression function, but I want to do it in a probabilistic sense. So I want to look at the equation on the top and agree that this is basically the likelihood of our model. Because already, if I go to the previous slide, I told you that the response at a given x is this Gaussian, right? Now I have given you n points, xn where the response tn is tn, so my likelihood of the model is the product of these Gaussians, right? Now, remember, when you write the likelihood, right, the assumption here is, if I knew what the parameters are, what is the likelihood of the data that I have observed? So if I knew W, if I knew beta, and you notice in the notation W and beta, I put them in the conditioning, right, as if I knew them. That's what the likelihood is. For a given model, if I know what W and beta are, then the response, I have observed xn and tn, so the likelihood is given by this equation. Now, is it important to actually write this precisely like this? The answer is yes. Because at the end of the day, when you start doing calculations, people need to understand, is W there a condition? Is W integrated out, or is beta integrated out? So you need to actually be very precise. All right? Now, the other notation here is, you notice there is a T bold, an X bold. This T bold is the vector of all the responses in my training data. My Tn, if I take T1, T2, T capital N, that's my vector T. And the vector X is all the inputs, X1, X2, X capital N. Okay? So these bolds are not by accident. Okay? So this xn is not bold, it's 1 point, n point, and tn is the corresponding response. W is a vector, all right? You can see it's bold, and beta is a scalar. So actually you may wonder, why do I take the same noise in beta? Because it makes life very easy. So you notice here, I'm assuming in the likelihood model that for each x, the response Tn, right, follows a Gaussian, but all of these are with the same precision beta. So the noise doesn't depend actually on the location, and statisticians will tell you this is not good, right? And indeed, it's not very good, but this is what we use. Okay? And if you learn more about regression, okay, you will, if you somehow want to make this noise to be a function of the location x, the models that you get, they are called heteroscedastic models. Okay, so think of heteroscedastic means models where the noise changes with the location. Here, that's not what we have. Okay, I'm going to take my log likelihood for my regression problem the same way we did for the Gaussian, right? Remember we computed the MLE estimates for mu and sigma squared for the Gaussian. So, you know, this, if you take logs, the product is going to become a summation. So you're going to get this wonderful thing here. Plus, from the normalization, you're going to get these nice things. So the first question we have to pose is, what's the MLE estimate for W and what's the MLE estimate for beta? Okay? That's what we did for the Gaussian. For the Gaussian, we asked, what is the MLE estimate for the mean and what is the MLE estimate for the variance? So we need to maximize the log likelihood, and immediately you can recognize the only place where W comes in is on this first term, right? There's no W here, so W comes only here. So if you want to maximize this with respect to W, it's the same as minimizing this square error that we saw before, right? So immediately you can appreciate that actually doing the MLE estimation for W should actually be the same as doing these squares. Nothing new, right? And you may say, so why are we doing it if it is nothing new? Because progressively, you know, we're going to start adding prior models and see how we can become fully Bayesian. But for now, maximizing the likelihood is the same minimizing the square error, the square loss function, okay? and so the MLE estimate would be the least squares estimate. And the beta comes here. So I'm going to give you estimates for the MLE for W and beta. Obviously, if you only look at these formulas, the next time you're going to have to do a trivial calculation of this nature, you will not be able to do, because you never did the calculation for this trivial problem. So you have to repeat these formulas, and you have to trust me. There is no algebra involved beyond what you see on the slides. You can actually look at it and say, yep, I understand. It's there. So the W, it comes only here. So instead of maximizing this, because there is a minus sign there, we can actually minimize this square. All right, so the MLE estimate for W is given here. And when you do the optimization with respect to beta, you get that the variance is the variance of my predictions, but with respect to what mean value? With respect to what mean value the model gives me, right? That's the regression function. So you anticipate basically this MLE estimate for beta to also have problems. All right, because this is, the empirical variance, but with respect to the MLE estimate in this particular case for W. Now, let me just tell you what somebody will do who doesn't like to do heavy calculations. All right? You optimize this, you minimize this with respect to W, and you get a least squares estimate for W MLE. All right? You calculate an MLE estimate for beta, and somebody say, I'm done. I don't want to do anything. And he's done because he's going to use the formula that you see at the end of the slide. So tell me, what is the formula at the end of the slide? And maybe we have already given a name to it before of this type of calculations. You remember the likelihood model? If you want the prediction at X, right, which is T, given the parameters, it's a Gaussian. But now you take these parameters and you fix them to what values? When you look at this formula the way it is, these parameters are fixed to what values? I see MLE, MLE, so what values are those? Well, they are the MLE estimates of the parameters, right? They are the MLE estimates of the parameters. So this is what we had called, I'm almost certain, in an earlier lecture, the plug-in approximation. So rather than treating the parameters W and beta as random variables, we fix them to certain values, and in this case, the MLE values, and then we use the likelihood model, right? So if somebody tells you, I want a distribution of responses, you say, you know what, let me calculate the MLE estimates. This is the likelihood, and the only thing I have to do is, for W and beta, I'm going to use their MLE estimates. Done. Unfortunately, this will get you in trouble if you have very few data points. So you're not done. Okay? You're not doing a good job. Okay? But certainly I want you to remember this is what is called a plug-in approximation. Plug-in is take your likelihood model and plug in the MLE estimates in your likelihood model, and this is what I have done here. But still, I want to formally write these equations for this W and for beta, so we can see how these equations look once and for all, and also to convince you why I call them least squares estimates. All right? Because you have seen least squares. I want to show you that actually this is a least squares problem for W. Okay. All right. So let me do some algebra. All right. I don't know if Nick did this, but So let me. I'm going to use the basis function approximation for my regression function. So my likelihood model, again, nothing new. It's the product over all my training data of these Gaussians. The mean is W transpose phi of xn. Xn is each of the training data. And the noise, the precision is constant for all of these different x's. So we're going to use the log likelihood. So we have exactly as before. And my parameters theta here is both W and beta. Nothing new. Okay? Instead of maximizing the likelihood, if you like minimization problems, you can actually minimize the negative log likelihood. So I introduced the notation that you will see in machine learning books. The negative log likelihood, NLL, is minus basically what you see here. Okay? So if we actually minimize this, I mean, basically by using a minus, that minus of the exponential of the Gaussian will disappear, right? So it makes the algebra a little bit better. But it's only to beautify the formulas. It doesn't do anything beyond that. All right. If you expand this log of the of these Gaussians, okay, so you can immediately see that this log likelihood is written these logs from the normalizing factors, okay, minus beta times this error function that we have seen it before, but now I formally introduce it explicitly here with some name, all right? So this is called E subscript of D of W. So now you're going to have to help me with the selection of the names, all right? What this D here means, from where the D is coming? I don't remember now, so you have to help me. Okay? So obviously this is, I minimize an error function, right? That's what it is. But what does, what is the D means? Nothing comes out of nowhere, right? Just my brain has stopped functioning right now. So check it out why there is a subscript D, okay? So again, when you expand this, right, from the exponential of the Gaussians, you're going to get this error function. This summation is what's called the residual sum of squares. So this is extremely important terminology, all right? So this is what the regression function does at each training data xn. And the residuals that you get at each xn is Tn minus the regression function. So this is the residual sum of squares, okay? Two things. I want you to appreciate that the errors, basically, this error function that we want to minimize to find the MLE estimate for W is this, we are trying to minimize these errors here. So if we're fitting, let's say, a straight line, the sum of squares is the sum of these lines. That's one thing. And the second thing I want you to pay attention is that if you actually try to visualize this error function in terms, in a schematic as a function of W, you actually get, if let's say you have only two W's, right? If W is a vector with components W1 and W2, what type of function in terms of W do you think this is? I mean, I can see here W and then squared. So what type of functions do you expect to get in terms of W? Like if I plot it in 2 dimensions in general, what type of functions are you going to get?
Parabolic.
Not parabolic, actually. I mean, what is the simplest thing you can expect? And next to the simplest. What's the equation of a circle? What's the equation of a circle? Yeah? We're on a tape now, right? So what's the equation of a circle in 2 dimensions? But what's the equation of a circle in W1 and W2? W1 squared plus W2 squared equal to what? To a constant, right? Okay? So that will be the easiest thing you will get, right? But in general, because you have this phi of x sense multiplied, you may not get a circle, but you may get W1 squared divided by something plus W2 squared divided by something equal maybe to 1 or a constant. What type of curve is that? An ellipse. All right? So now why I mention circles and ellipses, all right? Because immediately if you visualize this thing in terms of circles and ellipses, you know there is a global minimum for the error function. All right? So the nice thing with MLE is you can actually solve the optimization problem, and there are guarantees that you can find a global minimum, all right, for the error function, or a global maximum, if you like, for the log likelihood. This is using quadratic error. All right, now I'm going to do some algebra to show you that the relation of all of this with least squares. And I want you not to just look in the formulas and say, yes, I understand it. Go home and actually do the algebra because it's universal. It comes everywhere, okay, when you use basis functions. So we are interested to compute W first. That maximizes this log likelihood, where epsilon d is my square error function that you see here, okay? So now what I'm going to do is to do the optimization. You're going to have to take derivatives with respect to the vector W, right? Now, taking the derivatives with respect to a scalar is something you know. Taking derivatives with respect to a vector is something maybe you need to go and read on how to do it, okay? But literally, the way that I will do it is I will treat it as if it was a scalar and look at the equations and I ask myself, do they look nice? If they look nice, they must be correct. If they don't look nice, there must be a problem, okay? So if you take derivatives with respect to W, you know, you have this quadratic, so the 2's and 2's will cancel, so you get this minus that times, not phi, but phi transpose. Right, so I'm going, you remember, this is scalar, this whole parenthesis here is scalar. Phi is a vector, a column vector, phi transpose is a row vector. So really what I'm doing is I'm writing the gradient of the log likelihood as a row vector. If you want to write as a column vector, you know, you can take the transpose of this equation, but I am writing like that. So I'm expanding and I have Tn times phi xn transpose minus W transpose, phi of xn transpose equal to 0. All right? That's a nice equation. Beta is not 0, so immediately you can see an equation from there for W, but I wanted to write it nicely, and I'm going to, so this is the result actually, all right? If you solve this equation for W, you're done, but I wanted to do it nicely, and I'm going to do it nicely by defining first what is called the design matrix. Okay? And I want you to look at this design matrix for n training data, because the idea is universal for any task in machine learning. So look at the design matrix and tell me, so this is capital phi. Each row corresponds to what? How are you going to remember what each row is? Look at each row. What is each row? What is each row of this matrix corresponds to? Each data point. So each data point corresponds to every row. And what is each column corresponds? This is basis function phi 0, which actually, I forgot to mention, it's a dummy basis function equal to 1, because it multiplies W0, right? So W0 comes alone. Phi 1 is your first basis function, and phi m minus 1 is, let's say, the m minus 1 basis function. Okay? So each row, every data point, each column, one basis function. And actually, there is a merit to look at this equation in terms of rows corresponding to each data point, but it's also of interest to see this as each column that is one basis function evaluated at all the data points. So you can actually see the design metric says this new basis function, this basis functions, you notice it's a different phi. All right, I have this phi now, this sort of a calligraphic. This little phi here, this calligraphic phi, is a given basis function, let's say the function phi1, evaluated at each of the training data sets. Okay? So this is this capital matrix phi. If you put the algebra together, everything is on the slide, you can actually show that the MLE estimate for W is given by this wonderful formula, phi transpose phi inverse, phi transpose t. T is the vector of the training values, all right? And the inputs are coming inside the matrix phi, the design matrix. And don't tell me that this equation doesn't remind you exactly the least squares equation. Does it? Have you seen that equation before? I mean, I remember I was teaching this even on the engineering mathematics course a semester ago. And I bet none of my students even remembers that. Okay? So this is the least squares estimate, and it comes that the MLE estimate is identical. Okay? So the MLE estimate and least squares are the same thing, and they have the same pathologies that we discussed earlier with MLE estimates. Now, I already had shown you the MLE estimate for the precision, or this is, beta is actually the precision, 1 over beta is the variance, so the MLE estimate for the variance is the empirical variance, but again, notice that the mean that you use is the regression function, so it's not the true mean for the model. Okay? So we have MLE estimates, nice MLE estimates both for beta, and we have nice MLE estimates for W. General, I want you to remember that at least for the problems that we discuss, right, the optimization problem that you need to solve to compute W and beta is what is called a convex optimization problem, because the type of functions that you get, the contours or circles or ellipses, so they always lead to a unique globally optimal estimate. This is extremely important, because if you change sort of your model, you're not going to be able to find a global optimum for these MLE estimates, and that can have many issues. So I'm giving you some reminders here of what is a convex function, all right, or what the convex region is. I give you here a concave function and a non-convex region, so you can appreciate this function here that is not convex, it's not concave. You can see it has two minima at A and B, but they are not global minima. All right, so that can be an issue. So some functions that they are convex, they are e to so if the parameter that we're looking at is theta, for example, theta squared is convex, e to a power theta is convex, and theta log of theta is convex. And there is a reason I put these functions there, especially this function theta times log of theta, because this function theta log of theta will come everywhere when we discuss about entropy. Okay? So theta log of theta is a convex function, but log of theta alone is a concave function. Okay? That's as much as I want you to know about this. Now, somebody who likes mathematics, right, computes the MLE estimates with least squares, and it's done, right? But somebody will tell you, how about if I give you 10 million or a billion data points? Can you actually form that huge matrix and have a matrix phi that has 10 million rows? So the idea is, can you actually learn the the W that minimizes this error function, right? That's the MLE estimate. Can you learn it by using some ideas from what's called stochastic optimization? And I'm only giving you the formula, all right? Because I covered this in another course. So the formula, you can actually do the minimization here by this nice formula. So you can update the parameters from iteration tau to iteration tau plus 1, one data point at a time, all right? So this formula says, compute the gradient of this error for the data point n. And that gradient, right, is like you take the function 1/2 of Tn minus W transpose P of xn squared without the summation. You compute the gradient of this for that point, you put it in there, and eta is what is called a learning rate. Right? And there are methodologies that tell you what to select for eta. So when you compute the gradient of this error function and you put it explicitly here, the parameters are updated with this simple formula. Now, the only thing I'm going to say, and you need to trust me on that, is if you take this simple formula, even if I give you 1,000,000 points, it's very possible that you will be able to find the parameters correctly, even maybe after 50 data points. So you don't have to take all the data points all at once. One point at a time, and this idea converges. Now, this method is extremely powerful in machine learning and, of course, in deep learning. And at least in the context of this course, is called the LMS algorithm, least mean squares algorithm, the LMS algorithm. All right, so in cases where you have to minimize, you have to find MLE estimates, all right, and possibly map estimates. Somehow you can do the calculation, one data point at a time, iteratively, and this is the calculation that you see here, and the algorithm goes with the name LMS. Now, you can show actually that this literally will converge to the right answer, okay? But the idea is you don't have to use all of the data points. Okay, we have 2 minutes, so let me just tell you an issue with the MLE estimate and the square error function, okay? So you notice when we use a Gaussian for the likelihood, right, it leads us to the minimization of this. So think now of the following problem. Think that I give you some training data, all right? But I also give you some training data that they're way off, very wrong. This is what we call outliers. So when you look at this function, all right, so let me go back. All right, what it does is it computes the error between Tn and W transpose phi, and it squares that error. So if I have outliers, the distance of a regression function from these points is huge, square. And you know what that means? That somehow W will have to be adjusted and move towards these outliers, even though these points may be completely garbage and wrong. And this is what is happening here. If you look at the adjustment of the regression function here, a straight line, when I use my MLE estimate, this line you can see here has moved, instead of being somewhere here, it has moved towards the 3 outlier points. So how do you solve this problem? And again, I am not going to elaborate for this course. What you need to do is, instead of using a Gaussian likelihood, use a likelihood that doesn't have that square, the quadratic thing in the exponent, right? So something that does not lead you to this error function. Maybe instead of having power 2, you just have the absolute value there of the error. And what functions, what distributions do that? If you use a Laplace likelihood or a student T likelihood, you can see, even though you have outliers, the regression function doesn't change very much. Okay? So these other methods are more robust, basically, to they are more robust to the outliers. There are more ideas on how to correct this problem in the slides, so you can actually read more on those. Okay, so what I'm going to do is on Wednesday, I am going to tell you how regularization comes now. All right. So we are progressively moving towards a Bayesian framework for regression, but the first thing we did is we talked about least squares. We talked about maximum likelihood estimation. We discussed the two things are exactly the same. We looking at this slide, the maximum likelihood problem. It's a convex optimization problem, which is very nice. So there's always a global maximum of the log likelihood that you can find. And then I believe we talked about regularization in the context of least squares, right? So what we have not done yet is to talk about regularization and how it comes in a probabilistic framework. We have a newcomer once a while, just arrived. All right, so, okay, so, and also I remind you, if you want to do the MLE estimate one training point at a time, you can use stochastic optimization approximation. So this is steepest descent, and this method actually always works. So if you have thousands of data sets, you may be able to converge to the MLE estimate for W right away without having to go through the whole data set. And this method is going to come to be very important later on when exact approximations will not be possible, and it goes under the name least mean squares. So this algorithm that you see here is the LMS algorithm, so I want you to remember it. Okay. I think in passing, I mentioned that in the context of maximum likelihood estimation at least, that using a likelihood that is a Gaussian is not a robust method to outliers. And what that means is, if you remember a Gaussian, right, when you look at this likelihood model, the Gaussian has a term in the exponential that is t minus y squared, okay? So if you have outliers, like this point, so these are correct points and these are far away from reality, so the error in t minus y squared is very high, so it pushes the regression function towards the outliers. So this is what we say, that the method is not robust to outliers. So if you want to have something that is a little bit better, you're going to have to use a likelihood that does not have a square in the exponential, and a potential likelihood that I have here is the Laplace likelihood. Student T and many others may do the job as well. Okay, so this is not something to take lightly. So if again, in the presence of outliers, Gaussian likelihood is not going to do a good job. Okay, I don't want to elaborate much more on this subject for now, but each of these slides are not only to look at them. There is a computer program most probably. All right. So for those who are interested to learn, not just look at the slides, can actually see that the implementation of robust regression is just a few lines of programming. Okay. All right. So let me go back to the regularization, and then we will see how regularization may be able to come naturally in a Bayesian setting. So you remember, by the way, I was asking you what that D means in the error function that we had. Means data, because that square error, right, is basically the regression function minus the training data square. Okay, that's why there was a subscript D there. There is a purpose in life. So anyways, if you look at the classical least squares problem, is this term here. And we said that this is prone to overfitting, so we introduce regularization in this form. And there are many different ways of doing regularization that I will discuss today, but this is basically the L2 norm of W, and it says minimize this error, but at the same time, don't allow W to be too large, okay? And we said the regularization is not the same as the penalty method that you learned in other courses, all right? It's something completely different, okay? It's not penalty, it's regularization. So when you do the least squares problem, I think we discussed this last time, the estimate that you get is lambda I plus phi transpose phi inverse, phi transpose t, where capital phi is what? Remind me? What is capital phi? I forgot. Say it again? The design matrix, obviously, all right? And every row involves one data point and all the basis functions evaluated at that data point, okay? So capital phi is the design matrix, and I mentioned in the last lecture that effectively what this type of regularization does, this matrix is really ill-posed, so when you take the inverse, it will blow up. So effectively you regularize by adding a small lambda number, that's the regularization parameter, in the diagonal of phi transpose phi. That's a standard trick, okay, with this method. So this is regularized least squares, and in engineering and statistics, you may also find this with the name ridge regression. All right, so lots of times you may see comparison with ridge regression. It implies basically a regularized least square system. Now, again, we discussed this last time. The question will be, how do you select lambda? And you can actually try to evaluate how the model does on a test data set for different lambdas, and you will see there is a whole range of lambda values that actually this works well. So there is no one unique lambda, right? So lambda can be anything, let's say, from 10 to the minus 15 to 10 to the minus 6. It does the same good job. Whole range, okay? So, which makes the problem of computing lambda actually a little bit easier. But there are books written on the subject area, all right, that once upon a time I used to teach courses when there was audience to those courses, all right? In inverse problems, that's a standard topic, and so you can find more in the literature. Okay. Now, the regularizer is extremely important, and it will come naturally when we do a Bayesian setting. So I want to say something first in the form of regularization. I use Q equal to 2, which is the L2 norm of W, okay? But what I have done here is I extended the regularization to, so this in addition to the standard least squares problem, where I use a different norm, a Q norm if you like, where Q is 1/2, 1, 2, and 4, just for examples, and I plot different contours of the regularization potential if you like. So I am plotting this, all right, for different Qs. So the circles basically correspond to the regularization that we just discussed, the ridge regression using L2 norm of W. But this regularization using the L1 norm, if Q equal to 1, this becomes the L1 norm, is extremely important in machine learning. Extremely important. And I'm going to show you early on now why different types of regularizations have lots of implications. So let me show you graphically with little algebra, if possible. So remember, the problem that we have is to minimize this error function to find W that matches the data. So W transpose phi, right, is the regression function. We want to minimize this square error. And then we penalize the high W's, say keep them small for different Q's, right? So we use different regularizers. So the way I want you to look at this problem as an optimization problem is a problem of minimizing the square error that we had in the first term in the earlier slide. So this is my circles. If, let's say, I have two variables only, W1 and W2. So this is, again, that's how we got the classical least squares estimate, minimizing the error. So these are contours of this term here, all right? The first term only, okay? So the problem is the same as, let's say, maximizing actually minimizing the error, but with the constraint, all right, that you see up here. So I am transforming the addition of the regularizer to a constraint problem. I am saying minimize the error implied by the contours of that you see here in blue with this constraint. And you have to believe me, the proof is on the next slide, that this optimization of this whole functional that you see here is the same as minimizing the first term with the following constraint. So rather than adding this regularization term, is the same as introducing this constraint for some appropriate value of eta. Now, where is this idea that this optimization problem is the same as solving a constraint optimization problem? Well, you have to take an optimization course. Okay? And when you take an optimization course, you will most probably, in the first lecture on constraint optimization, you will learn about this type of analysis. So again, rather than minimizing this, you can minimize the first term with a constraint that says, all right, that this norm has to be less than some constant to be computed. Okay? So you trust me now that that's, let's say, it's fine. So what I have done here, I plot this constraint. All right, so I am plotting this constraint for different values of Q. So what Q do I use here? Q equal to 2, so that's my L2 regularizer. And what do I plot here? I plot Q equal to 1, that looks like that. Now, why this graph is extremely important, all right, is if it doesn't say on the slide, you have to tell me. So why this slide is very important. What's the difference that you see? So you want to find, all right, you want to minimize this, but with a constraint that is given by the domain inside the circle, right? So you have to be somewhere either inside this domain or on the boundary, and the same thing here. So what do you see different from here and there for this simple schematic? I mean, if you look at Q equal to 1, what do you see from the schematic? Graphical. So this regularizer looks exactly like that, okay, even in high dimensions. So if you think like circles or spheres trying to reach that constraint, where are they going to reach that constraint first? If that constraint has these edges. Where are they going to reach the constraint?
On the boundary.
On the corners. All right? And if they reach the constraint on the corner the way that you see in this picture, what does that immediately implies? Implies that W1 equal to 0. And why W1 equal to 0 is important? What does that imply? Implies that out of the two variables, there is only one active variable. So if you use this type of regularization, what does it do to your problem? What does it do to the W's? What's the buzzword? Which is a huge area of research. Say it again? Introduces what?
Future extraction.
Future extraction, not quite. So with this, some of the w's come to be 0, right? They're forced to 0. Not all, some. So it says not all w's are active. And remember, every w multiplies a basis function. It's like saying, I don't need that basis function p1, right? That's what w1 equal to 0 means. Or I don't need w5, right? So I don't need the function phi. Okay? So what does that mean? This selection of which w's are needed and which are not needed, and the rest are 0. What's the word that we use for that? So we say that this methodology introduces sparsity. It leads to sparse models. Okay? And this is extremely important because if you do regression and you have 500 basis functions because the problem is very complicated, high dimensions, you cannot really do analysis with 500 basis functions, but if you use L1 regularization, it will say a lot of them are not needed. You don't have to say it, the methodology will actually force that. Okay? And this method, in a deterministic setting at least, goes under the name Lasso. Okay? And if you search on your web, since you're constantly in your computer, you will see that Lasso has, a few millions of citations. Okay? And it's an algorithm that has impacted all areas of engineering and the sciences. Okay? So at least if I ask you at the end of the semester what is Lasso, don't tell me it's something from a Western movie that you saw when you were a kid. Okay? Because everything is possible in this life. Okay? So that, please don't tell me that because I may have to retire prematurely. Okay. So obviously we suppose to spend 2 or 3 lectures on sparsity later in the semester, but now you can see how these methods actually may be coming, and so you sort of have some sense just in case we don't reach that point. Now, the proof that this original problem, minimizing this with the regularizer, it's the same as minimizing the first term with this constraint. The proof is in one slide, okay? And so you can read it, or you can go to Wikipedia and search for constraint optimization and Kern-Tucker conditions, and you will see there is nothing to it, okay? And it is a very important problem because not just in this case, but many problems are constraint optimization problems. Okay. All right. So what I'm going to say now, before we start moving to the Bayesian case that naturally leads to regularization, I want to talk a little bit about the extensions of this likelihood model that we have discussed. Okay, in the case where the target is not a scalar but it's a vector. Okay, so let's say that for a given x, an x is a vector, right? So it can be a very high dimensional x. You predict an output, okay? That's my likelihood model, but this output now, t, it's a vector, right? So you do simultaneous regression of many variables, all right? So for a given x, you predict t1 and t2, t3, etc. So do not confuse this t, the way that I have it here, with the training vector t that we had in the earlier part of the slides. So the idea here is the response is a vector. So for every input you get a vector t, and that's the likelihood model. And I want you to look at this likelihood model and compare it with the one I introduced many times in the last lecture, and tell me what is how this model differs from when the prediction is scalar. Tell me everything that is the same and everything that is different. Because obviously it's a model, you can do something else. So what do you see that is the same of this with the case when t was a scalar? What is the same as what we did before?
The mean is the same. The mean is same.
The mean? No, but I see now there is not little w. That w is a matrix now. All right? So let's not start with the mean, because the mean is not the same. What is the same, looking at this likelihood? What is the same with the previous models we had? Is the variance the same? I mean, this I there is a matrix, right? But the variance obviously is the same for all predictions, right? For all variables. Okay? So we are taking literally here that this is a diagonal covariance with the same precision beta for all variables. And the other thing that is the same, we're taking the same basis functions, all right, that we had for scalar prediction. So the basic functions are exactly as before, nothing new. The only thing that is new, instead of, if I put the little vector W there, W transpose phi is a scalar, right? That would be the mean value, but this T is a vector, so we put W transpose phi, where W is a matrix, all right? Is a matrix. So if I have, let's say, my response is k-dimensional, and I have m basis functions, the matrix W is m by k, so W transpose is k times m, so W transpose phi gives you a vector of order k. Okay? So again, the base functions are the same. You can do regression on multiple variables, but we take the variance to be the same, and you basically don't need me to compute the MLE estimate for capital W. All right, so what you need to do is take the log of this, take derivatives with respect to this matrix, take derivatives with respect to beta, set them to 0, and compute. Okay? Now, if you don't know how to take derivatives with respect to matrices, okay, the painful way to be to take derivatives with respect to the components of the matrix. But once you get convinced in the results that you see, for example, in Bishop's appendix on this type of problems, you manage to take derivatives directly with respect to matrices. All right? It would be very painful to work with components here. Okay? So if you write the log likelihood, okay, this is what you get. Nothing new. This comes from the square of the Gaussian, and this is from the normalization factor. And so the MLE estimate for the matrix W is this wonderful thing that looks like these squares. Okay, these squares, but now this instead of having a vector T, remember in scalar regression, this capital T was little t that involved T1, T2, Tn, right? The response was scalar. So this was from my training data. But now the response is a k-dimensional vector, so this capital T is n times k. Apart from that, this matrix looks, this equation looks identical to least squares, and it is least squares. And I can tell you, there's some discussion on the slide. Actually, doing the formulation that I highlighted here is literally the same as doing k-independent scalar regression problems. So basically, this looks a nice formula, but when you look at it carefully, you realize it's the same thing as doing, the prediction of each column of the matrix W one at a time using the vector tk, which are the response of the kth, the kth response of t over all the data set points 1 to n. Bottom line is, right, that if you do this, you don't earn anything. It comes out that the results are basically running k-independent scalar regression problems. So somebody will say, okay, this is not good, right? I'm not learning anything here. How do I extend this? And you may immediately say, I can use the same regression model, but instead of having the same variance, maybe I can put some covariance metrics that now couples the variables. What do you think? Will this fix the problem? So will the regression problems now become coupled, you think? If instead of having beta minus 1i, if I put some covariance metric sigma to be computed, will this make the problems coupled? So it comes out, if you write the log likelihood, obviously now you're going to have to take derivatives with respect to W, derivatives with respect to sigma, you set them equal to 0, and it comes out that the estimate for the matrix W is exactly the same as before. So W does not get affected whatsoever from the presence of that covariance matrix. That's a surprising result, okay? And of course now you have to compute an MLE estimate for sigma, and that MLE estimate for sigma is given by this nice formula that is actually nothing else but the empirical covariance. You don't have actually to do any calculations to compute sigma, because if you look at this equation, this looks to me like the log of a multivariate Gaussian. So to compute sigma, you know what it is? To compute the MLE estimate of a multivariate Gaussian, which is the empirical covariance. All right, so this equation looks like it's the log of a multivariate Gaussian. So if somebody tells you find the sigma that maximizes this log likelihood, is the MLE estimate for sigma of the covariance of a multivariate Gaussian, and is given by this nice formula. So I want you to remember that if the response is not scalar, but it's a vector, you're going to have to do something more sophisticated to actually correlate the responses, okay? It's not as simple as effectively saying I'm going to use what we learned in the class, and extend this to k variables and put some covariance. It just doesn't work, okay? It looks nice, but it doesn't do the job. Okay. I actually don't need this. I'm going to bypass this so we can go to some directly to where we need to be. So let me go to slide 40, which is backwards. And don't look in your computer screens. That irritates me, by the way. When you have 5 students in the audience and everybody looks at the computer screen, it's like talking to my Uncle Bill. And I don't have one, okay, with the name Bill, okay? So, I remind you how our likelihood model looks like for scalar predictions, okay? So we effectively said the response at every point x is a Gaussian, okay? And centered around the regression function calculated at x 0, okay? And so that's our likelihood model that we use to do all the analysis, okay? And if you remember this very nice error we got, this square error that we got from the training data, okay? That's basically where the MLE estimate for W comes from. Okay, so I want you to remember this slide, that when I use my likelihood model and likelihood being a Gaussian, I get basically this square term, okay? So don't forget. So this is from the log likelihood, you get this error. All right. Now let me go to slide 77. And we're going to start becoming a little bit Bayesian, okay? And what means a little bit Bayesian? So we're going to keep the likelihood model as it is. So at every point, the response is going to be a Gaussian centered around the regression function. But now I am going to put a spherical prior on the regression coefficients W. So I am going to make them random variables. So when I say the regression function is W transpose phi of x, now the W vector is a random vector, and I'm going to take the simplest possible form for the prior, which is a spherical Gaussian, and I call it spherical because, even though W is a vector, the precision or variance here you can see is constant in every direction, okay? So I write this as, I'm expanding the Gaussian, and it looks like this. And obviously W is m-dimensional, so I get something nice like that. Everybody agrees? Right? I mean, I'm writing down the Gaussian for the prior of W. Okay? And remember, so that we don't forget, alpha is the precision of the prior, and what is beta? The precision of the likelihood. Okay, so alpha the precision of the prior, beta is the precision of the line. Okay, so if we have a prior model, all right, we have a likelihood also, all right, that's my likelihood here. If I multiply them, I get a posterior for W. And again, the notation is not to just look at it, but is to understand it, right? This is the posterior, and what is capital X and capital T is my training data. And what is alpha and beta? Alpha and beta are hyperparameters that for now I take them as constants. All right? I mean, I said here is the precision of the prior, right? Beta is the precision of the likelihood. I haven't said anything how to compute them, so we take them as constants. So the posterior of W, given all of this, is the likelihood times the prior. Don't read what it says on the footnote. I'm going to come back to it, if not today, tomorrow. Okay, so I don't want to do the algebra because I don't think it is in the slide, since the algebra is trivial. You remember the log likelihood, when you take the log likelihood, you remember that it contains that square error of how my regression function, what error, how well it approximates in the square sense the training data, all right? So when I get the log of the posterior, I will get that error from the first term, and what will I get from the prior when it comes to W? There will be a term that involves A over 2 times W transpose W. Everybody says that? When you take logs, right, you add the log of the likelihood, which is what we have seen before, and the log of this, which will give me A over 2 W transpose W. Okay? So let me concentrate on computing now the map estimate only. All right? So we are not going to do full Bayesian analysis. We're going to compute the map estimate. The map estimate will be basically finding the W that maximizes the log posterior, and the log posterior will involve this term here, all right, plus the square error that we had before with the beta parameter coming in. So would you agree that when you try to postulate the map estimate, if you reverse the signs, the problem is the same as minimizing this error? From where did beta in this term comes? They comes from the likelihood, right? Beta is the precision, so it's there. Where this thing comes? It comes basically from the exponential that you have in the Gaussian for the prior. So you're looking now to find the map estimate. You're looking to find a W that minimizes this. And if you look carefully, you will immediately recognize, if you were here on the last lecture, that this problem is regularized squares. I mean, we did this today too. The only difference is that instead of having the regularization parameter lambda that we had here artificially, right? Now you can see that lambda naturally comes to be the ratio of the precision of the prior divided by the precision of the likelihood. So suddenly, what people were doing in mathematics for half a century with regularization methods can be recovered as the map estimate of a Gaussian likelihood with a Gaussian prior. Very nice, right? And now you may look at it, right? But I remember, maybe 15, 20 years ago when you were going out presenting this thing, people from least squares communities and inverse problems, they would say, wow, how is that possible, et cetera, et cetera. But, 5 years later, everybody became Bayesian and doing very sophisticated things, and many people got out of business because this paradigm basically includes many other things that people were doing for almost a century. Okay, so this is the map estimate, right? And it doesn't mean the map estimate is good. It's a point estimate. It is the same as regularized least squares. It's not approximately the same. It's the same. It's identical. But it requires a Gaussian likelihood and a Gaussian prior. All right. Now what I'm going to do is, and I am sure when Nick gave his lecture, he went through all the proofs, right? So I want to compute the whole posterior and do the algebra. And again, if you look at this slide, and you don't use your little hand to actually do the calculations, the next time you have to derive the posterior for another problem, you will not be able to do it. Okay? And you will not do it at all, thinking there is no closed form solution. Okay? Very many problems in statistics, you start with something simple, and believe it or not, you can actually find very nice closed solutions. And in this case, obviously, Gaussian times a Gaussian, yes, of course, you will get a nice solution at the end. So here is my prior, right? That's my prior. That's my likelihood. Okay, so I multiply them. So I have this exponential times that exponential. So basically, I can put this in the same exponential. And there's a square there, so I can expand it. So obviously, I'm going to get a W transpose W. And I'm going to get, there is a term that involves only Tn squared. And I don't bother with terms that don't involve W. So that's why this says proportional. So I only keep the terms that have W on them. All right? Only keep the terms that have W. Now remind me, what is the close the square technique? What's the idea? Close the square that I mentioned once or twice before. So we're going to try to put this in a nice form, because the way it is there, it's not very appealing. Okay? So what is the close the square? I mean, I look at this equation, right? It has W transpose times something times W. And this is W transpose some vector plus some constants, right? So when you see W transpose times a matrix times W, what does that tell you? You forgot, I mentioned this, closing the square. What's the idea? What is the form of a Gaussian in general? Can somebody spell it for me? Of a multivariate Gaussian. In the exponential, what do you have? You have some quadratic term in W, but so you have W minus the mean transpose times the inverse covariance times W minus the mean. So closing the square means what? Trying to add some terms that don't depend on W, so you can get that quadratic form and reveal what the mean is and what the covariance is. All right? And actually, literally, if you want, you can say, I am going to write this term here as W minus something times some matrix times W minus that something. And let me figure out what the covariance of that something, that mean is. That's what closing the square is. So I am not going to do the algebra because there is no algebra, right? There is no algebra, okay? And so when you close the square, miracles happen, and you get an exponential that immediately tells you that this posterior, all right? So multiplying this prior with this likelihood, all right? So we have to multiply the two things together. I'm sorry, yeah. So this is the prior, this is the likelihood, right? The likelihood expanded like this. So if I multiply the log of this with the log of that, all right? Or here I keep the exponentials. I should not have done that, but it doesn't matter. So if you keep the exponentials, you immediately recognize that the result is a Gaussian that has this nice mean, okay? And this covariance. And what is the covariance? Is given by this wonderful formula. And actually, you notice it is the inverse covariance that comes from this nice formula, not the covariance itself. Okay? Which means that if you need to do calculations involving the covariance, you're going to have to invert this massive matrix. Okay? So you compute Sn, and once you know Sn, you know what the mean is. Okay? So let me remind you all the symbols. What is beta?
Prior
What is beta?
Covariance of the likelihood.
Is the precision of the likelihood. Sn is given by this wonderful formula, where alpha is the precision of the prior, and phi of xn, remember, are the vector of all the basis functions evaluated at the data point xn. Okay? So again, so effectively, phi of xn is a column, so is phi of xn a column over or a row of a big matrix phi? Obviously, it cannot be a column, because when you traverse the column, you go through every data point with the same basis function. So if phi is a column vector, right, phi transpose is the nth row of the design matrix. All right? So this phi transpose is the nth row of the design matrix. Okay. So we have a wonderful form for the posterior of W, and it's given by this covariance matrix, okay? And here is the answer for the inverse covariance, and it's given by this mean. So if you want to find the map estimate for a Gaussian, the map estimate is the same as the mean. So the map estimate is actually given by this nice, wonderful formula. And here I am writing them in a compact form. Instead of using the basis functions, I put directly the design matrix phi. And you can see why the design matrix comes so naturally in this problem and every other machine learning problem, right? Because this matrix phi summarizes all your information about your training data together with a vector capital T, which is the responses at the corresponding axis. So phi summarizes the input transformed by the basis functions, and vol T is the responses at these input points. Okay. I mean, a nice homework will be, okay, and I don't need to assign you a homework to do homeworks, okay, but a nice homework would be, well, look, can I actually take a very general prior, and instead of taking a diagonal covariance, just take a very general covariance S0, and instead of taking a mean W, right, can I put an arbitrary mean there? Would that still give me a nice answer? And the answer is yes, absolutely. And here are the answers. So repeating the same calculations and closing the square, the posterior of W is a Gaussian with a covariance Sn and a mean Mn, the same as the map estimate, given by these wonderful formulas. And again, if you think these formulas are complicated, you will be surprised to see that as you extend this model to realistic cases, you will still be able to get closed form solutions, but they will look messy. Messy analytically, but computationally, even if I give you a messy equation, it may be one line of programming, literally, if you do it right, okay? But these formulas certainly look very nice. Okay. I'm not going to do the proof for this case. It basically, you just write down this prior times the likelihood that we had before, you multiply them, you close the square, and there's the answer. Okay. Maybe I did not emphasize this in this course, but hopefully you learn this in other courses. This Bayesian formalism is sequential in nature, right? So practically all the calculations can be written down as updates from the calculation. Let's say if you have n data points and you estimate the map, you estimate the posterior of W and you compute Mn and Sn, and now you say I want to update these values of Mn and Sn when a new data point comes. You can actually write the calculations that you saw in the previous slide in an incremental form. So if you know the mean with n data points, you can actually compute the mean of the posterior when you have n plus 1 data points. That's the only effect, right? You just add the term. And you can do the same thing for the precision. You just add phi transpose times beta, And that's a very powerful thing, because if somebody gives you 1 billion data points, you don't have to go and say, take all these data points, form this huge design metrics, and do all of this. No, what you can do is start working one data point at a time. All right? You find the mean, you find the covariance, a new data point comes, says update, and and keep going that one data point at a time. Okay? Very nice, basically, way to implement it, and obviously this makes sense if you have, let's say, data that are coming dynamically, right? You collect them in time, so these update formulas are very nice. All right, so let me give you some up to now with the posterior to see how these results look like. So we're going to take a function that, a true function that is a straight line, okay? And we're going to, let me see, we're going to select the parameters, some fixed values, minus 0.3 and 0.5. And I'm going to give you some training x points, all right, that I select them uniformly between -1 and 1. And then I'm going to add some noise to the measurements of those inputs x, and that noise will have a standard deviation of 0.2. So effectively, I am going to use a precision beta for the likelihood that is 1 divided by 0.2 squared. So it's the precision is 25, and my precision for the prior is equal to 2. Just to keep the discussion going, right? So I'm going to fix basically alpha and beta. Can somebody, by the way, tell me in a forthcoming lecture, how are we going to compute alpha and beta if we don't like fixing them to some arbitrary out of nowhere values? What's the buzzword? What is the method that will tell us what alpha and beta will be? Since I taught that lecture. So alpha and beta are like hyperparameters coming in the prior. So what do we do with those? What is the method? Hierarchical Bayes, exactly. So we're going to basically compute the marginal likelihood, maximize it with respect to alpha and beta, and it tells us exactly what the optimals alpha and beta are. So nothing is being lost, right? We're doing baby steps to learn what's going on, but so if you're bothered that alpha and beta here are fixed, just don't worry. We will be able to actually compute correct values, okay? But right now we want to understand what this posterior model does for us. Okay, so again, this is the true solution, right? A straight line, and we provide some data with some noise, and we want to see how this, the posterior of W will look like. So I'm going to start with the prior first, right? So no data, and don't ask me why, but one of the students who developed this little MATLAB code for this example that is out of the Bishop's book, he somehow plotted this prior, the contours, with horizontal and vertical axes that they don't look the same, even though the size is from -1 to 1, all right? So these contours, I want you to think of circles, all right? They're circles, okay? All right, so you are looking on two variables, right? W0 and W1, so they are circles, okay? So can you tell me, it says here, yxw, using samples of W from the prior. So how exactly are you going to generate all these nice lines? You're going to have to take samples from where? From a two-dimensional Gaussian, this prior Gaussian. Right? So basically, you need to be able to sample from a prior, right? It's a Gaussian, one line of a computer program. Let's say if you use MATLAB, you sample from this prior, and for each sample, your regression function, right? Your regression function will be W0 plus W1x, right? I'm using basically the simplest possible regression model, so it will be W0 plus W1x, okay? And you see now, all these realizations of the regression function are all over the place, all right? This is important, right? To have this plot, it shows you they're all over the place, but they're all basically regression solutions. These are all solutions. Okay, they are all correct. Okay? Now, let's say that I am going to provide you one data point, and this training data point is there. Okay, so what I'm going to do is I'm going to write the likelihood for that training point with a Gaussian. I'm going to multiply with the prior. I'm going to get, so this is how the likelihood will look like. Okay, and then I'm going to multiply this with the spherical prior, and the posterior with one data point will look like this. These are the contours of the posterior. So what I'm going to do is now, I'm going to say the posterior is a Gaussian. Easily to take samples from this Gaussian, I take samples and I plot the lines W0 plus W1x, where now these W's come from the posterior. And you notice, I didn't force this, but all of these lines are moving closer and closer to the data point that I have, right? They don't pass from that data point, but they're, all of them somehow out of nowhere, they're moving in that direction, okay? But, you know, they have multiple different slopes, right? Because I only have, I mean, you can see to fix a line, you really need two data points, okay? You cannot take one data point and fix it, and obviously something like that makes sense. All right. The next time, I'm going to have another data point, and I want you to think the sequential nature of Bayesian. So this is my posterior. So when I start using the next data point, this posterior is actually going to be my new prior, right? And then I'm going to multiply with the Gaussian likelihood for the new data point, and I'm going to get the new posterior. So let's see how it looks like. So one data point and another data point, and the lines now look way better, right? They seem to be actually passing close to the two data points. And more importantly, the fact that I have these lines all over the place, it has to do with the uncertainty in W, right? And you notice the uncertainty in W, it went from this huge variability that you see there, or the right plot in the middle, to this variability that is much smaller. So two data points and the uncertainty in W gets smaller and smaller. If you use 3 points, look at the uncertainty in W, right? It becomes very small, and now all the lines look very nice. Very nice. Okay? Very nice. All right, and here is all of the results together in one plot. All right? And so the idea here in a Bayesian setting, there is no such a thing as S solution. All of these lines are good, right? Because they all together, they tell you that there is some uncertainty in W. That uncertainty in W leads to various regression functions that you may want to fit the data, and you can see some samples of those in this plot. All right, and I think that's another implementation coming out of Kevin Murphy's book, basically solving the same problem, okay? And so you can consult that. Okay, now, if you compute the posterior in W, you are not doing anything that is Bayesian yet. Because somebody will tell you, W has no physical meaning, right? There are coefficients, some regression function. I don't care about W. So what do you care if you don't care about W? You care to have a model that is capable to do predictions for you. Once you train it, you say, for this X, can you tell me what the response is? Right? That's when you become Bayesian, right? So once you train it, you say, for a given X, tell me what the response is. So effectively what you need is, you need to be able to predict, to do predictions for a given new X. You see that on bold X is a test X, is a scalar, a new X, and you say, can you tell me what the distribution of T is, given bold X and bold T? So this is the posterior predicted distribution, right? Given the data that allow me to calculate the posterior of W, I want now to say what the response is at a given little x. Again, pay attention, what is bold has to do with training data. What is unbold here has to do with test data, okay? And I'm doing this 1 point only for the testing, all right? So x here, I'm writing it as a scalar, and the response also is a scalar. Now, you maybe forgot, but this is your standard equation for calculating You can derive it in half a line using the sum and product rules of probability. This is the formula for the predicted distribution. And what is the formula says? Given the parameters, take the likelihood of observing t at x, right? That's this term. Multiply that with what? What is that? The posterior, and then integrate the parameters out. Okay? And again, I want to emphasize, only when you compute this integral in W, you can say that you're doing Bayesian analysis. If you don't, you are just basically dressing up things with probabilities. There's nothing Bayesian in what you do. Obviously this integral in general, right? We may say if W is a million dimensional, you have to calculate these integrals. That's painful. People don't do it. But I can tell you, 99% of lots of problems I know, somehow this integral can be done analytically. And if it cannot be done analytically, we already have learned other methods to actually do it. Can you remind me one method that may allow you to compute that integral? Laplace approximation, for example, right? You can go and say, for example, if your likelihood is Gaussian, and this thing is whatever it is, maybe you approximate it as a Gaussian, and then there is an analytical formula. Okay? All right. So, is there any hope to... So can you tell me, we discussed about the closing of the square. Can you tell me what is the idea to get a closed form solution for this? So this is a Gaussian. The posterior is a Gaussian, and we have to integrate W. So we have closing the square. So tell me now, what is the trick that you're going to have to use? Because I'm not going to do it for you. I'm too tired to go on algebra because you start sleeping on me. So what's the idea to get this integral on W when you multiply a Gaussian with a Gaussian? It's related actually to closing the square, but before we wanted to close the square to find what the mean and the variance is. Here we want to close the mean, we want to close the square to do what? We have an integral in W. So if I had the exponential of something that looks like a Gaussian, right, with the right mean and a variance that we can identify, and we integrate in W the exponential, what is left when you integrate the exponential of a Gaussian? So if inside I only have the e to the minus x minus mu transpose, some covariance inverse, x minus mu, what is left? So when you compute that integral, obviously it's not 1. What is that integral? The normalization factor. All right? So, and the normalization factor of a Gaussian, you read it from the books, ready to go. Okay? So, so that's one way to do it. And, there are the formulas I'm going to show you now, they use this trick, right? But once you verify them once, all right, so you have to verify them home once. If you don't verify them and you copy them from different versions of Bishop's book, you will realize different typos here and there, and the rest of your life you will be publishing results that they are wrong, okay? And there may be even typos on my slides still, okay? Intentionally, okay? So what you can do is, Bishop has shown the following extremely handy results using the trick that you just described to me, okay? Effectively closing the square and computing the normalization factor. And these results, you can prove them using this closing of the square and the normalization factor, but I want to state them because they are very handy in thousands of different applications, okay? Very handy results. So let me just tell you what they are so you can use them in different settings. So let's say that x and y are vectors, right? And p of x is given by this with some mean and some precision matrix capital lambda. And I also know p of y given x, another Gaussian. And I call this linear Gaussian models because you notice this conditional has a mean that's a linear function in x. That's why I call it a linear Gaussian model. And those models come very often, even when you do unsupervised learning, These are the same formulas we will use, okay? So again, I give you P of x, this formula, I give you P of y given x, with the mean being a linear function of x, and a different matrix there, L, okay? Then you can show with the closing the square ideas that you can actually, multiply those together and integrate in x, right? So if you multiply them, you will get the joint, and then if you integrate x, you can get P of y, and it's given by this nice, wonderful formula, right? You cannot immediately see that the mean of y is a mu plus b, right? Okay, from there, all right? It comes a mu plus b, but the covariance is a little bit more complicated, and if you want to use Bayes' rule, and instead of having P of y given x, if you want P of x given y, you can actually solve that you get this wonderful result, analytically. I am just telling you, these formulas, if I'm you, I will just cut a piece of paper and post them on my desk, because if you actually do calculations, this is what you need to use daily. Okay? So, now why I can use this, you remember my original problem that I highlighted was to compute this integral of this likelihood times the posterior and then integral in W. The likelihood is this nice Gaussian, and the posterior is given by this wonderful formula. Can somebody actually tell me, looking at this, remember here I had P of x and P of y given x, and this conditional has a mean that is linear in x. Can you look at these formulas, the second and third row, and tell me what is x and what is y in my problem? Right? If I'm going to use these formulas, what should I use as x and what should I use as y? I mean, look at the, so here I have the likelihood, okay? P of t given x and w. And you notice the mean is linear in what? The mean of that likelihood is linear in what variable? The mean of t, right, is linear in what variable? In w. So w plays the role of x here. All right? And you can see actually, to use those formulas, you will need to have P of x. Do we have P of x? Of course we have. We have P of w is given here with this mean and this covariance. So actually, if you use these analogs, you can immediately, out of nowhere, do any calculations you want to, including, computing the predicted distribution, right? And actually, I did not put the conditions here, so you may want to take a note. I did not put the conditions on the predicted distribution because, as you can see, there was no room in the slide. Okay, so I cut it. All right. So you remember our conditional distribution had lots of nice arguments. All right. P of t, this is the predicted distribution of the little x given my training data. So now, this is my predicted distribution. A wonderful formula, all right, that tells me that at a given x, it tells me, by the way, you notice x here. It's not the training data. This is my test point. At a given x, it tells me what the mean is, which is this nice formula, and it tells me what my uncertainty, it tells me what the variance is. Okay, so you can see the formula summarized clearly in this slide. All right, so the predicted distribution at a given x has a mean mu of x and a variance s square of x. I'm taking here that little t here is a scalar, and here is the variance. All right, and I remind you what the Sn is. We calculated this from the posterior of w, and here's what the mean is. Wonderful formulas, right? I mean, if somebody tells you, do a prediction of the given x, it's a Gaussian. I mean, you can immediately say what the mean is going to be. Immediately you can say plus minus one standard deviation. Everything is there. And you notice the mean and the variance depend on x, which is nice, right? So it basically tells you that as you move different prediction points, right, that the variance and the mean will change. So let me I'm going to give you some graphical results here. So before, let's say we compute it for a given, so if you use an nth order polynomial to fit this data, and you fix the parameters alpha and beta, as we discussed, you compute the posterior, you compute the predictive, and here is how the results look like. These blue lines, all right, are my training data. What color is this other line? What color is this?
Red.
What is it?
Red.
Red? Really, it's red? It doesn't look red to me at all. Okay, so let's call it red. So this is the mean of the predicted distribution. And what is this? This is the exact function, that in this case is a sine. Okay? So at any point, so if you want, somebody tells you, can you tell me at this point what the best prediction is? You're going to say, that's the mean, all right? And then you say plus minus that. Okay? And in this picture, maybe it's not obvious, right? But the error bars are not the same for different x's. I mean, in this case, the training data, they were everywhere in the domain, so the error bars look the same. But I will show you an example where the error bars really look very much different. Okay, so before I show you actually this, let me emphasize two results without proofs. They are in the slides. If you get some formulas, you should always say to yourself, is there anything I can prove that actually can give me some confidence maybe that these things are correct, right? I mean, obviously there is many tests you can do, but are there any obvious things that you anticipate? So let me ask the following thing. If sigma n plus 1 is the variance, sigma squared n plus 1 is the variance when we have n plus 1 training data, do you expect this to be true? Do you expect the variance as you add more data to get smaller and smaller? I mean, are the error bars going to start shrinking? They better shrink, right? So you can actually show, and the proof is given in the next slide, that these nice formulas that I gave you actually satisfy this equation. Now, a second trick. If you had an infinite number of data sets, will the error go to 0? Are the error bars going to go to 0? If I give you an infinite number of data, will the error bars go to 0? What do you think? Remember the problem when we started, right? We said the response is this regression function plus some noise defined by that precision beta. So the best you can do in the error bars is what? Is defined by beta. So the best you can do when n goes to infinity is this thing has to go to inverse beta. So there is nothing, if you do any calculations and your error keeps going down, down, means somewhere you must have put a minus sign that makes that to happen. You cannot go lower than 1 over beta. And the proofs are actually, this particular proof I think is a little bit tricky. You can do it in one slide. The second proof is trivial. And they're given on this slide that I'm not going to elaborate, but at least you know that the discussion is on the slide. Okay, so let me, so before, with the error bars looking the same because we had too many data points, what I'm going to do is I'm going to do the calculation of the predicted distribution one data point at a time so we can see what's going on, okay? So if you only give me one data point, all right, remember this curve that you see there, and again, I don't know what color it is, let's call it orange, all right? So that curve is the exact solution. So if you give me one data point, all right, the mean will be that straight line, okay? And this, two things define the error bars, and you can see away from the data point, the error bars go to infinity, right? That's what you expect. If you have a method that away from the training data, it keeps the error bars the same as close to the data, means you have the wrong method. If you don't have data, the uncertainty should go up, and that's exactly what is happening here. The uncertainty is going up. Now, if you had 2 data points, suddenly you notice from having this uncertainty only minimized here near the data point, now you have a whole region that has practically similar error bars, but then away from these 2 data points, you get a situation that looks like that. And if you keep going like this, we have a situation exactly with what we saw in the earlier slide. Okay, there's something else I wanted to show you. Oh, this is a very important slide. Remind me, what's the plug-in approximation to the predicted distribution? You know, when I introduced something on earlier lecture, I said we will need and we'll come back to it, because I even defined this in the introductory lecture. What's the plug-in approximation to the predicted distribution? You remember the predicted distribution is the integral of W of the likelihood times the posterior dW. So to get the plug-in approximation, what do we use? We use the likelihood, but for the posterior, what do we do? We use a point estimate, which is either the MLE or the map estimate. So we approximate the posterior with a delta function. So, you know, let's say we use the map estimate, but it says here the MLE estimate, okay? You want to make a difference, okay? So we use the MLE estimate here. So effectively, if you want to make predictions at the little x, all right, given all your training data, you will get literally the likelihood, which is a Gaussian model, but the W will be fixed at the MLE estimate. Extremely easy, right? I mean, everybody can do this in online. But immediately, when you look at this, what do you observe? That the error bars are everywhere the same. And as a matter of fact, can you tell me these error bars are defined by what parameter directly and only? By beta. All right? Because that's the noise in the likelihood model. Okay? So this is a ridiculous model because somehow you notice away from the data, it says that the error is as confident as close to the data. Cannot make sense, right? You know, so if you see something like that, you know there is something wrong with the model. If you actually try to use the full predictive distribution, you can see immediately that away from the data, the error bars increase. I mean, you can still do predictions, but you say, look, I'm not very confident. If they are what they are, there's nothing I can do. This is the best I can tell you. Okay? Can you tell me these plots that you see on the bottom, what are they? I mean, one thing is to you know, so before, you know, I already showed you this, right? I showed you the regression function for different W's. So this is the regression function, all right, computed for different W's, and this W is your sample from where? From the posterior. In this case, I only show you one curve. Why is that? Because the W is what? It's fixed at the MLE. All right? So you can see, if you are looking to see how, if you like, the response at two different x's correlates with each other, this is the type of plot you need to do. This diagram there, it tells you the uncertainty at each x. This type of plots with lots of samples of the regression function, it tells you, you know, if I want, you know, if I take 2 points, it effectively tells you how the uncertainty at the 2 points relates to each other. It tells you what is, you know, how the response at two different axes correlate with each other. Okay? And I'm going to come back to formally show you this with a formula, obviously, tomorrow. Okay? This is the same result, so I don't need to, you know. All right, it's 1:45, and what I want, I'm obviously going to finish here. Before, you know, we move to more complicated Bayesian regression problems, way above, you know, what we have covered up to now, I want to make a connection of what we have learned up to now with kernel methods. I'm going to show you a trick on how you can take these simple Gaussian models and actually immediately realize that you can actually formulate them without using any basis functions, using what's called kernels. Okay? And that sort of will introduce a plethora of solutions beyond what somebody can use with Gaussian basis functions or polynomials or sigmoids. And this will be by introducing this equivalent kernel representation of the Bayesian models. Naturally, when you use prior models, and then so we discuss about the simple Bayesian model for regression and Gaussian likelihood, Gaussian prior, and we produce the posterior of W, we produce the predictive distribution. So now I want to actually extrapolate a little bit and show you that somehow the equations we got may lead to new ideas that somehow have a lot of legroom in machine learning. So this will be topics to see later on in the course, but I wanted to bring to your attention now that we do the simple regression models. Okay, so if you remember, we finished by writing down the predictive distribution, and the mean of the predictive distribution was given by this nice equation. If my pointer works, okay? So this is the mean of the predictive distribution, and I'm writing it. Mn is, by the way, just a reminder, is the mean of the posterior of W, okay? So if you substitute the equation we had for Mn, you get something like this. Phi is the design matrix, and if you write actually the product phi transpose T explicitly in terms of this basis phi of xn. So remember, phi of xn is really it's the nth row of the design matrix, all right? It's the nth row of the design matrix. So I can write phi transpose T like this. So yada, 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 this equation here gives me an explicit form for the mean of the predictive distribution. So if you want to do predictions after you train the model at a given point x, the mean is given by this equation, okay? Very nice analytic form. Now what I want is to look at this equation and try to see if we can somehow potentially later on generalize things. So notice that this whole thing in the brackets there is a function of x and xn. And actually xn is also contained inside that variance matrix Sn, because that contains the design matrix phi. But certainly I can take this whole bracket and write it as a new function that has arguments x and xn. Okay? So again, this whole thing, I'm going to call it the kernel k x comma xn. So it's a function that has two arguments, x and xn. All right. So if I rewrite the predictive mean then takes the form summation over little n over the training data of k x comma xn times tn. So I want you to look at that equation and tell me what does it tell you, basically? It says to do predictions at x, what do you need to do? Look at this very simple equation. So to do predictions at x, what does this equation tell you to do? You remember Tn are, my training data, right? It's my function estimates, if you like, at points xn. So what does this equation tell you? To compute the response at x, what do you need to do? There is no time, right? So take all the responses for all your training data and weight them with this kernel that, as we will see, somehow accounts for the distance of x. Well, not quite, but sort of, you can think of this as a distance measure between x and xn. So effectively, you can think this equation as weighting the responses, accounting how far is your point x from the training point xn. Can you see that? So, you have response at different points, and you want the response here. Obviously, you anticipate the training data points close to x to be more valuable than far away. So the anticipation is that this is what the kernel does, okay? So this equation itself literally introduces a whole new way of actually doing regression, where effectively you take all the training responses and you weight them appropriately. And those methods go under different names, including smoother regression models, okay? But you can actually find books on that subject alone, all right? So we can actually think that we don't really need any Bayesian regression, because somehow we can take all the training data, weight them with some kernel, all right? But remember, in this case, the way that I derived this equation, we started with the Bayesian formalism. We computed the predictive mean, and then we call this the kernel. But now I want you to imagine, maybe, you know what? Maybe we should forget all of these things. Maybe we should forget this equation, and we should forget the basis functions, and rather than start directly with this equation, where k is some appropriate kernel. And we will see later on that the choices for k can be infinite. And you don't need to start with basis functions to define kernel. You can postulate directly different kernels, right, and see how well this approximation weighting over all the TNs with this kernel x, n does. All right, so let me try now to give you some intuition why I said the response at this point looks to depend more on the training data that they're close to that point. So if we use Gaussian basis functions, right? So if my phi is Gaussian basis function, so the k here is computed with Gaussian basis functions, and I plot this k based on this equation, this definition, right, that bracket. If I plot k as a function of x and x prime, you realize, looking at this plot, that the kernel takes the biggest values when x equal to x prime. So when x is far away from x prime, this thing is very small. Okay? And so the intuition here is that the points Tn that contribute to the response at the point x are the points that they are close to x, are the training points that they're close to x. Can you see that? I mean, that's a common sense thing. That's what you like this to look like, okay? So actually, what is also very interesting is, even if the basis functions that you use here don't have local support, when you do this calculation and you compute this kernel, k, it comes out from this plot that you see here that the kernel has local support. If x is far away from x prime, it's 0. Right? So effectively, even though this equation says take all the TNs and weight them and average them, all right, the idea here is all the xn's that are away from x don't contribute anything. So you can actually do an averaging, weighting average locally. Okay? All right. Now, by the way, you can actually prove, right, if these are weights, right, in some sense, they have to be normalized weights. So if you take the summation of that kernel for a given x, for all training xn points, so if you sum the kernel for all x and for all n's, obviously the answer is going to be equal to 1, right? And you can show that. Okay, now, if I plot it actually in a more clear fashion to see that these kernels are localized, so what I'm going to do is I am going to take in the two plots that you see, on the left I fix x equal to 0.3, on the right x equal to 0.5, and I plot the kernel value as a function of x prime, and you can see that the kernel basically picks up at x prime equal to 0.3, all right?
And in this case, the kernel picks up at x prime equal to 0.5, exactly as we expect. Okay. We have discussed about all of this. So let me now, so obviously I'm not going to tell you today how you can start directly with the kernel without any basis functions, because this will lead to another series of lectures. And if you search on Google, you will see there are hundreds of books on kernel methods, because it's a huge subset of machine learning, okay? I just want you right now, because we did regression, to think that this concept of using basis functions may not be necessary. Maybe you can start directly with kernels that do exactly the same job. And we will see actually that leads to a much richer way of doing certainty regression. So let me do the following calculation to give you now the physical meaning of what the kernel is and relate this thing back to some of the plots that I showed you in the last lecture yesterday. So let me take the predictive means at two different locations, x and x prime, and I would like to calculate the covariance, how they correlate with each other. Do you remember graphically, how did I tell you that you are going to, if somebody asks you to plot something that measures how y of x correlates with y of x prime, how are you going to plot this? What are you going to plot? I mean, one of the plots we discussed was plotting the mean and the error bars, all right? That will not do this. So how do we evaluate how y of x correlates with y of x prime? What type of plots can we do? We only discussed two types of things you can plot, right? And one of those was to actually plot the regression function for different w's coming from where? From the posterior, all right? So that's the way if you want to actually visually see how y of x and y of x prime correlate. So let me do a simple calculation. This predictive, I'm going to write down y of x and y of x prime, all right? You remember my regression function is phi transpose w, right? And y of x prime will be, I just write it the other way around, the same thing. I write it as w transpose phi of x prime, okay? These are scalars here. The way I have it, this y there is a scalar response. So if you want to calculate the covariance of y of x and y of x prime, you have to calculate this covariance. And I'm not going to prove anything here. If you don't know this, you can actually expand, use the definition of the covariance. You can show the covariance of this is the same as phi transpose phi x prime on the sides. On the middle, you put the covariance of w. And the covariance of w, we're going to use the posterior covariance of w is Sn. And somehow, if I go back, since you forgot, this phi transpose Sn phi of x prime, by definition, is beta minus 1 times the kernel xx prime. Again, the algebra is on this one equation, but the bottom line that I want to emphasize is that if you want to see how y of x and y of x prime correlate to each other, it comes out that the covariance is proportional to the kernel. So when you hear kernel kxx prime, what does it actually measure? Because somebody will ask you this tomorrow, and you better know. So what is k of xx prime? What does it measure? I mean, x and x prime is only the inputs. So somebody will say it's a distance between the input points. Well, not quite, because this is equal to that. So k of xx prime, what does it measure? There is no difference. It is the covariance. It measures how the response, the output at the points x and x prime correlate to each other. So even though K of x prime is really looks like a measure in the input space in X. It actually gives you how the output correlates at the 2 points. This is extremely important. So when later on, when we do, let's say, Gaussian processes, okay, you will see, this in every slide. The kernel, it looks like a distance between x and x prime, at least when we wrote the weighted average of the responses to compute these predictive mean, if you like. But you can see here, this measures the covariance between y of x and y of x prime. Okay? So we have a physical meaning for x and for the kernel x and x prime. And I want you to remember this, because if you don't, we will be in trouble. Okay. Let me just, so there will be no details or anything about kernel methods. I want you to, I'm going to give you sort of something to maybe think about, okay? So so in our case, right, using the basis function approach, the kernel between 2 points, I call the x prime here z, so between 2 points x and z was this by definition. So notice, if I define this function here, so if I define beta 1/2, all right, Sn, square root of Sn times phi of x, you can show that the kernel, can you see, right, if this is your definition of psi, can you see that this kernel is psi transpose psi? Right? And when you see psi transpose psi, what does it remind you? When you have a vector transpose with a vector itself, what is that? What type of operation from linear algebra this reminds you? I'm looking for something more powerful. Close, not distance yet. Close the inner product, thank you. All right, so these kernels, all right, the way that you can start, you can take the inner product between anything, and you can show it's actually a well-defined kernel. So all the kernels basically have the form of an inner product the way that you see here. Okay, and there is a whole sort of steps that we will discuss in another lecture, that if you start with one kernel, you can define millions of other kernels based on that. Okay, and so this concept of kernel design, it's very big. So you can start with something simple and make it way more complicated. But for now, I only want you to remember that somehow you may not need basis functions on anything we are going to do from now on, and somehow maybe kernels can be used. That's one thing. And then if you want to start with kernels, the place to start is to take some inner product form for some vector psi of x. So if you postulate some psi of x, anything, so for example, psi of x can be just x. So the inner product can be x transpose z. That's a very nice kernel. All right? Okay? And again, it gives you the impression, because it's an inner product in the input space, that has something to do with distances in the input space. The interpretation of kx of z is it captures correlations of the output at the points x and z. That's the wonderful thing with kernel methods. Okay, done. So I need to now go and correct some of the things we discussed about regression models. And this is what actually I will describe today. It's something you need to do in every aspect of your training data in any machine learning algorithm. So I'm going to discuss this in the context of regression today, but the same thing you have to do it in every other problem, okay? Even if you read books and it doesn't say anything about it, the idea is this is your pre-processing stage that you need to do. All right, so you remember, when we wrote down the regression function, we started with some coefficient W0, and then we had W1 times some phi1 of x plus W2 phi2 of x, etc., right? And usually you put, because you want the equation to look nice, you put a function phi0 that you make it equal to 1, so you can write the whole thing as W transpose phi, the vector phi, right? So that way, that's what we did up to now, right? We had a very nice equation, so we don't have to worry about, W0, treating it separately. Now, there is a very tricky part is that when it comes to overfitting, W0 doesn't contribute to it, which means when you're going to do regularization or you're going to put priors, trying to introduce regularization through priors, you should not penalize, basically, you should not do anything to W0. So yes, the equations before were looking nice, we got uniform, nice results on everything, but somehow we need to get rid of W0. And what I mean get rid, we need it, but we should not do the formal calculations that we did, to, including W0. So how are we, so I have to tell you how to do this, and the answer is very simple. It's actually, what you need to do is you need to center your input and output data. That's all, okay? But that is easy to say. The answer is, why does that solve the problem? Okay, so I'm going to show you how and what type of calculations are implying. That, if you look at them and you understand them once, right, you don't really have to worry all the time. You just enter the data, and you can follow the equations that we have in the next few slides. So let me do the following first. I'm gonna take only this, this minimization problem of this quadratic error that we have seen coming both. Look at this, just comes directly, let's say, from maximizing the likelihood, okay? So this is what we get. So I'm going to minimize this by taking derivatives with respect to W0 and Wj. And usually, that's how the least squares problem comes, right? That's what we did in the earlier lectures. But right now, what I'm going to do is I split it, the W0 from all the other Ws. I'm going to take derivatives with respect to W0, set them equal to 0, and yada, yada, yada. After one line, that's the answer, all right? And the answer is this T bar and phi j bar are the averages of the responses and the averages of the basis functions over all training data points, all right? So there is nothing extra in the derivation beyond what you see on the slide, and this is the answer. W0 is the discrepancy between the average of the target values Tn, all right? And these are the weighted averages of the basis functions averaged, as you can see here, over the training data points. Obviously, this is a nice formula, right? It involves the average of T and the basis functions, but also notice you cannot do this calculation unless you have computed the Wj's, all right? So it is not something that you can use in the beginning and say, this is W0. No, you cannot do it because you first need to compute this Wj's there, okay? If somehow we can compute the Wj's on their own, then this equation will give us what W0 is. So the question is, how do we compute Wj's on their own? Now, I have the complicated sort of version of this, and then I have a simple 1D regression problem with a simple version of it. At least the equations look a little bit simpler. So let me do the complicated case, okay? I'm going to do the complicated case. So what I have done is, again, I'm looking at the likelihood. You remember, so I have a bunch of training data, all right? And phi times W accounts for, that's my design metrics. So rather than having the product of, of W transpose with the basis functions, I write this as phi times W. And I write the W0 separately on its own. So notice this equation, the way I have it on for the likelihood, right? Maybe we have not seen this explicitly because before we will calculate the likelihood for one data point, then multiply with the next data point. So what I have done now is I put all of this together in this wonderful, wonderful vector form. Can you actually appreciate that if you take this transpose that, every term in that inner product will be the likelihood from one training point? Yep. So I am writing this in a compact form like this, okay? And again, for convenience and following the literature notation, I call the W0 mu, like the mean, if you like, of my regression function. So when I look at this likelihood, it obviously depends on this mu, and I need to do something to get rid of the mu. I need to be able to compute Wj's alone without the mu coming in the picture, all right, without the mu. So that way we can do whatever we can do, even Bayesian analysis, without worrying about the mu. So the idea is very simple. This mu, right, the average of my regression function, we're going to assume it, that can take equally any positive or negative value. So we're going to put a prior on it that is a uniform prior, right? So we're going to put a prior that's a uniform prior. And then guess what? We're going to use this equation, all right? And effectively, we're going to write the joint distribution of T and mu, and we're going to integrate mu out. So what I'm going to do is, notice here, in my likelihood, there is no mu. This is the marginal likelihood. And what you see here is my likelihood, the joint, is basically the joint distribution of T and mu times the prior of mu, which is 1, and then I integrate mu out. And this equation looks complicated because I subtracted and added the average of T for a reason that we will see shortly. So there's nothing, this equation is identical to what I had before, times a uniform prior for mu, and then an integrally mu, so I can compute the marginal likelihood. And then I subtract it, and I added this T bar times 1n. 1n is a unit vector that has all ones, all right, of dimension n. So if you call this vector here an A, all right, so you're going to have A minus this and A minus that. And if you do the calculation with the transpose, I am going to tell you that one of the terms disappears. And I'm not going to go in the algebra. If you look carefully on the slide, it is obvious. All the algebra is here. This second term is going to disappear. Okay? And how about this term? Can you tell me what's going to happen to this term when I integrate it in mu? Like the first term. What does the first term remind you when you look at it? I see a mu minus T bar square d mu. So what is that term that reminds you? This first term. What does it remind you? Say it again? A Gaussian with a center around T bar. And that is, what will it give you when you integrate it? The normalization factor, which is another constant, we don't care. Okay? So that constant is out, okay? Because really we want to keep things that they have some functional dependence on W, And that's why I put things proportional here. So what is left is really e to the minus beta over 2 A transpose A, and I write this explicitly like that. We're done. You know why we're done? Because look at this. Two things. This matrix phi, the way that I wrote it, if I can go back, the way that I introduced my design matrix phi, I do not account for the bias there. So the phi includes only the basis function phi1, phi2, etc., right? Not the W0. So the phi is really the design matrix for my real basis functions, not phi0 that's equal to 1. And now look at that. Here I have t minus t bar times the unit vector. So effectively, if I center the measurements t, all right, if I center the measurements t, and I call this again, I don't want to use another name, if I call this again t, doesn't this problem looks exactly like the likelihood we had before in our calculations? Like when we included everything, like everything we have done up to now involves a likelihood like this. But this likelihood now does not involve any W0. It doesn't involve any mu. How did we get this, right? So the design matrix does not, involves only the basis functions phi1, phi2, etc. And the t that you see there, it says center t. All right, so from all, if you take, let's say, measurement T1 minus the average of all the t's, T2 minus the average of all the t's. So if you center your t's, effectively the problem, the likelihood of W looks exactly the way we have done it before. So now you can go and put a prior on W, you can compute the map estimate, the predicted distribution, you can do anything on this W, but this W involves only W1, W2, etc. It doesn't involve this W0. So when you compute W, let's say if you compute the MLE or the map estimate, then you say, and what is now W0? Because obviously you need W0, and the answer is W0 is T bar minus this weighted average of the average basis functions. Okay? So in all machine learning algorithms, you have to do this, all right? You have to be very careful what you regularize. So the idea here is if you center the data, the problem actually looks exactly like what we covered with some algebra that you don't have to repeat all the time, okay? And then when you finish computing this W, you can go back and compute W0 by minimizing the error function with respect to W0. And I have a trivial version of this, just in case you find this algebra with a uniform distribution on W0 messy. And here is a trivial problem. If you, let's say you have an X, it can be high dimensional input vector. So no basis functions here. I am writing my regression as W0, the regression function, plus W transpose X. All right, so my error function looks like this. So first, if I can compute this W, all right, that does not involve W0, then W0 will be given by this formula that we discussed before. No basis functions, right? It's directly X there. And let me show you how the W can be computed. Like, let's say the MLE of the W's. If you go and subtract, so notice from this formula, all right? From this formula, W0 is T bar minus X bar transpose W. So what I do is I substitute the W0 with what it is equal to, and then I combine Ti minus T bar, and then I should actually put a minus sign there. I should make it to look nicer. Minus sign of W transpose Xi minus X bar. So immediately you can see you have to do two things. Center the output. If you center the output and you center the input, all right, you have to center the output, you have to center the input, then the problem becomes actually your standard least squares problem where the design matrix involves center axis, and the output involves center T's. I mean, the equations look identical. They are the same. The only difference, instead of saying x, you say x minus the average of x. Instead of saying ti, you say ti minus the average of t's. And this is your standard least squares estimate. But this, so I'm using capital X here for the design metrics. This matrix involves xi minus x bar, okay? And tc is ti minus t bar, okay? And this comes basically, you rename this as ti, you rename this as minus xi, all right? And you get your standard least squares problem. And once you compute your w's, you can come back here and evaluate what the W0 is. So always you need to do some pre-processing of your input and the output, and there is a reason for that. So you should definitely not regularize W0. Okay. I'm going to finish this lecture by telling you about the predictive distribution in a full Bayesian setting.